Today we're going to start discussing some details about the phosphorus industries, including phosphoric acid production and phosphate salts production. The typical minerals of phosphorus in the nature are calcium phosphates, and the main ore for that is apatite, which has the general formula of calcium phosphate with some fluoride, hydroxide, or chloride impurities. It exists usually in surface mines, can be exploited with open cast mining techniques, and it can be purified using magnetic separation to isolate magnetic iron oxides, or flotation to isolate silica, and then calcination to get rid of any organic impurities. Phosphorus content in this is typically reported as a percent of phosphorus pentoxide, and typically the feasible standards for production are around 50%. The main chemical that we will discuss is phosphoric acid, which is mainly used for production of fertilizers and in detergents and water treatment, as well as animal nutrients production. Let's get started with production of phosphoric acid. The main production technique uses wet process, which includes the digestion of apatite with sulfuric acid. The phosphate portion of apatite reacts with sulfuric acid to produce phosphoric acid and calcium sulfate, and the fluoride part, or the halogen part in apatite, usually produces byproducts or impurities that include HF, can be removed as gaseous SiF4 in the presence of silica, then absorbed in scrubbers as aqueous hexafluorosilicatic acid, which can be used for water fluorination purposes. The other impurities, including other ions like iron, aluminum, uranium, can be partly precipitated with calcium sulfate, while the organic impurities, which can cause black color in the product, has to be completely removed in the pre-treatment processes. The calcium sulfate dihydrate, which is gypsum, can be used in building industry. Depending on the types of calcium sulfate precipitate, we'll have different types of processes for the production of phosphoric acid, and that depends on the type of the crystal that will form, whether it's calcium sulfate dihydrate or calcium sulfate hemihydrate. When the hemihydrate is precipitated directly and filtered off, that's a different process than the precipitation as dihydrate that can be subsequently recrystallized as hemihydrate. And the third variant of this process is precipitating an initial hemihydrate crystal, then recrystallized as the dihydrate.
The properties of the calcium sulfate byproduct is very crucial, especially the crystallinity of the product, because it affects its ability to be filtered, which is very important for the efficiency in the yield of production. The incorporation of phosphate ions into the crystal lattice of calcium sulfate reduces the phosphoric acid yield, and it also affects the ability of the product to be filtered and renders the byproduct unusable for building purposes. As we said, we have 4 different processes: 1 dihydrate crystallization process and 3 variants of the hemihydrate crystallization process. The most widely used process is the dihydrate process, in which the calcium sulfate is crystallized as the dihydrate in a temperature range of 71 to 85%, which results in an acid concentration between 28 and 32% with a yield of up to 93%. However, the calcium sulfate produced is not usable for building purposes. The hemihydrate process can take place in 3 variants. Variant 1, the digestion step takes place in a temperature range of 91 to 99 degrees Celsius, and then the hemihydrate is filtered directly without recrystallization, and that allows the production of an acid with the concentration of 45 to 50% with yield between 91 and 94%. However, the calcium sulfate byproduct is not usable for building industry as well. The second variant, digestion takes place at much lower temperature, 60 to 70%. However, recrystallization from hemihydrate to dihydrate takes place at 90 to 99%, and that allows the production of a little bit lower concentration between 30 and 40%, but increases the yield to above 97%, and the byproduct is usable for building purposes. Variant 3, digestion takes place at much higher temperature, between 90 and 99. However, the recrystallization takes place at much lower temperature, around 60 degrees, and that allows to obtain an acid with higher concentration as high as variant 1 and higher yield as high as variant 2, and also the byproduct is usable for building purposes.
Dihydrate process, as we said, the reaction usually takes place at temperatures around 80 degrees Celsius, and the ore and sulfuric acid are fed from separate feeds. And in this process, cooling is required to ensure the temperature is constant because the reaction is exothermic. These measures enable a uniform growth of the calcium sulfate dihydrate crystals, which is really crucial for the efficient filtration of that byproduct. This flowchart here summarizes the process. As we said, the apatite is fed from a different feed from the sulfuric acid into the reactor, in which digestion takes place. gas byproducts are removed into scrubbers, and the calcium sulfate dihydrate is filtered to be removed and washed to recycle any dilute phosphoric acid into the reactor again, and the filtrate will contain the product acid with concentrations between 28 and 30%. For the hemihydrate process, we have three variants as we mentioned earlier. Variant 1, the digestion takes place between 90 and 100 degrees Celsius, and the hemihydrate is directly filtered off, and that gives a concentration for the produced acid between 45 and 50%. But the yield is much lower. Variant 2 and 3 increases the yield. For variant 2, the dihydrate is obtained first at degrees between 60 and 70 degrees Celsius, and then the filter cake is recrystallized to the hemihydrate form by slurring in sulfuric acid at temperatures around 90 degrees Celsius, and that produces phosphoric acid with concentrations between 33 and 38% with very high yield. In variant 3, the hemihydrate form is produced instead at temperatures between 90 and 100 degrees Celsius, and then it gets recrystallized into the dihydrate form upon cooling between 50 and 60 degrees Celsius. The main advantage of this process is that the phosphorus pentoxide that remains in the calcium sulfate byproduct is less than 0.3% due to the efficiency of the recrystallization. And the yield of the pentoxide is higher than that with the dihydrate process, with concentrations as high as variant 1, which means it's going to be higher than 40%. This is a flow chart that summarizes the hemihydrate. Apatite is fed into the reactor, and sulfuric acid is injected to digest the apatite ore. Then the reaction mixture is filtered. The temperature of the digestion step has to be controlled through vacuum evaporation coolers, and then the efficiency of the process can be improved by recrystallizing the hemihydrate precipitate. So the recrystallization from the hemihydrate to the dihydrate form efficiently removes any phosphoric acid from the precipitate, and that phosphoric acid can be recycled back to the filtration step and then recycled back to the reactor tube. And the filtered off calcium sulfate dihydrate can be isolated and utilized in building purposes. Concentration is really essential for the different applications for that acid. For fertilizer production, for example, requires acids between 40 and 54%, and for transportation purposes, the concentration has to be increased to 50 to 72%. Obtaining that high concentration cannot be done using evaporation processes because it becomes problematic, because as you increase the concentration, the corrosiveness of the acid increases, and also it could lead to the formation of some precipitates or the release of acid-containing gases that contains fluorine or phosphoric acid mist. And also it's a very energy-intensive process. The wet acid can be purified by depositing the impurities as insoluble impurities as sediments, and also in order to facilitate precipitating impurity ions like copper and arsenic, that this can be precipitated as sulfides, while any sulfate impurities can be precipitated by adding barium to precipitate it as barium sulfate. An alternative for increasing the concentration of the acid is the multi-stage liquid-liquid extraction. In this process, there are three types of extraction agents used. First type is the water miscible agents such as methanol or isopropanol. Second type is the partially miscible agents such as butanol, isoamyl alcohol or N-heptanol. And the third type is the water immiscible agents such as tri-N-butyl phosphate or diisopropyl ether. In this process, the organic phase is gonna be able to extract pure sulfuric acid out of the reaction mixture, and the aqueous phase will contain acid solution with impurities. The pure acid can then be recovered from the organic phase by stripping with water and distilling off the solvent. The strongly contaminated acid remaining after production of the pure phosphoric acid can still be used for fertilizer manufacture.